Hello all. In this small part of lecture, we will look at the vector calculus part. We will review the Einstein notation and the simple products and how Einstein notation is used in proving some of the identities and which can help us further in derivations. Okay. To start with, okay. So when we think of vector has a magnitude and direction, as we already talked about in the class. If you write v this or v underscore, these can be called as these are known as Gibbs notations, and if you expand them, they have three elements along each unit vectors, and they could be represented as this, or you can represent it like this. It's all the same. 1 2 3 can represent Cartesian, cylindrical, spherical, wherever. So it's more general to write in numbers. In a compact form, you can write, or as a sum, you can write v is equal to sum of vi ei, and this I goes from 1 to 3. In Einstein or index notation, you can simply remove the sum and write velocity as vi ei vector. But if you don't want to be too explicit, what is generally done is you can just write it as vi. So, and throughout this course, we'll follow this notation, because we'll soon realize that if we carry this along, the derivations will become really bulky, especially when the tensors are involved. So whenever you see a standalone vi or vk somewhere with the free index, these are called free indices, but you can assign them any index you want. Here we can write, if vi or vk is written somewhere in the calculation, in the derivations that will come below, it means that it's a vector v. Okay, so this is our notation that we'll follow, and this is generally followed in books. One example of many is from this J.M. Powers book of mechanics of fluids, that you can expand a as this and then write, and for simplicity you can just write ai. Okay, simple properties of addition and scalar multiplication. I mean this is basic stuff, but I'll just cover it. V plus w is, is w plus v. This property holds. V minus v is 0. Scalar multiplication, if you have any real number multiplying or a combination of numbers multiplying a vector, you can play around with them. You can write alpha beta into v, or if alpha is multiplying v plus v at an addition of vectors, you can write it as alpha v vector plus alpha w vector. Okay, let's come to the inner product. It's also known as the dot or scalar product because it yields a scalar property or a scalar quantity. So consider v and w as two vectors, and they are usually commutative. V dot w is equal to w dot v, because in the end what you get is a scalar. One can write, if you can expand these, if you can expand these, you can write it in the expanded form. Each element would multiply. So vx wx plus vy wy plus vz wz is the what you will get. If you go from your high school notation, it would be the magnitude of v multiplied by magnitude of w into cos theta, which can be seen physically as an area of a rectangle, where one side of the rectangle is the v vector or any of the vectors, and the other side of the rectangle is the shadow projected. The length of the other side of the rectangle will be the shadow projected by the other vector onto the first vector. Okay, so this is one way of interpreting the scalar product. Why is it done? I mean, one nifty calculation is that it will help you prove the scalar triple product just by physical intuition. We'll come to that. Okay. Now, coming to the index or Einstein notation, you can expand v and w as v as summation vi ei, and then w as summation wj ej. You can write all of these two as different indices, but just keep them separate so that you can later merge them. So let's say you chose j for this and I for this. So you write summation, the two summation in I and j, and then the vector, the dot product between the two unit vectors has to be respected here, and then you have these scalars multiplying vi wj. Now this ei ej dot product, the two unit vectors dot product, can be called as the Kronecker delta, which means that if I and j are going to be equal, it's going to be 1. if they're not equal, is going to be 0. As we saw in the class, if ex dot ex is 1, ey dot ey is 1, but ex dot ey, they are not, they are 0, because they're orthogonal to each other, right? So we can simply write this as the Kronecker delta, and what this says is that if I'm here and any adjacent quantities that are multiplying me, we must make I and j indexes equal, because they have to be equal, otherwise the sum will be 0. So what we can write here simply is that vi wi. So it becomes summation over I, because summation over j becomes useless, and summation I vi wi. Now we make it another make it more convenient by just saying that we are going to assume in our notation that vi means a vector, wi means a vector, and v dot w can be represented as vi wi. So again, to repeat the rules, if the indices are repeated in an expression, they should be summed. That's what we saw. So this would be v1 w1 plus 2 w2 plus v3 w3. If not, let's say if you see somewhere standalone vi, or if there is a free index, for example, if you have v multiplying w dot, v dot w multiplying another vector a, then you would write this as vi wi into ak, because you don't want to write vi wi ai, because that won't mean anything, because the dot product is between these two, v and w. So you write vi wi, and then you write a k, aj, al, am, whatever index you want to give. Just don't give I, because then that would be confusing, right? So what I mean here, if you see something like this, and if this is the repeated index, okay, it will be some, this is a free index, that means this whole thing is a vector decided by this ak. Okay, again, some simple properties. If you have a vector dotted with a sum of other two vectors, you can just expand it. So u dot v, it becomes u dot v plus u dot w. If you have a scalar multiplying a dot product of vectors, you can simply just absorb it in one of them, or you can write v dot alpha w. Simple stuff. A magnitude of a vector is always greater than 0. So this is the v dot v is either equal to 0 or greater than 0. This is v dot v square. Sometimes you might also see in this textbooks as v square. Okay, so now the question is, the two questions that I ask you, you have to think about them, that does u dot v multiplied with w, does this equal this? Of course not, but you have to think a bit about it though. So the dot product is not associative in this way. Is it distributive? Certainly it is, right? We already saw above. Okay. All right, so let's talk about cross product briefly. If you have two vectors v and w, so in your high school format you can write it as magnitude of v, magnitude of w into sine theta, and multiplied by a unit vector which is perpendicular to the planes of v and w. Okay, so this is your, in physical sense, your one vector, this is another, so the third vector will be perpendicular to it, and the angle between them is theta. The length of this vector will be determined by the magnitude of this this cross product. Okay, another physical way to interpret a cross product is that you can consider these sides and complete this and extend this, or sort of copy this to make a parallelogram. The area of the parallelogram will be the vector cross product, or the magnitude of this cross product. Okay, coming to the Einstein notation now, you can again expand the v vector and the w vector, and this becomes the two summations in j and k, because this is what we assign to them, and we assign different vectors. We cannot assign the same vectors, because then it would be the dot product, right? Now, so v has ej vector, and then w has the ek vector. They have to be crossed, and the scalars can be written outside. Now this yields to the this gives us the Levi-Civita tensor, and it could be written as summation over I epsilon I j k e I. You might also see this version in the textbooks instead of this epsilon I Levi-Civita tensor k. I'm sorry, epsilon I. Sorry about this. Epsilon I. Sorry. Epsilon j k I e I. But these two are the same. We'll see in a moment because they involve two permutation changes that yield the same thing. So you may see either this or that. Now, okay. So you have this. Now what you can do is take this summation I outside so that you see that summation nicely as epsilon I j k, summation over I j k as well, wk vj into ei. Okay, using Einstein summation we get rid of all these bulky summations, and what we get ultimately is epsilon. What we get is just this part, that the cross product between them. Here it is. V cross W, we assigned J to it, we assigned K to it, and we said that we are going to name the overall vector as I. This is what we decided already in this whole process. And ultimately one gets epsilon I j k Vj Wk. The new index as the first one, the first cross product vector here, the second cross product vector here, Vj Wk. You can also write this as epsilon I j k Wk Vj. I've just done nothing. I've just replaced this. I've taken this here. So the relative positions of these things don't matter here, right? In Einstein notation, you can just jumble them around. What matters is the index and its repetition. Okay, J, K are called repeated index. I is called the free index. And this is a vector. Okay, I remember in the class towards the end when I was rushing, I asked you to do an exercise that take two vectors V and W and let them be A, B, C, W, B, P, Q, R, and perform a cross product between them, and do it your high school way and do it this way. My goal was not to suggest that this is a better way of doing the usual cross product. This is the shortcut way, and that there is a reason why this is followed, because this will give you this will take a lot of time, because you have to write it as the following. You have to write it 1 2 3 v2 w3 plus epsilon 1 3 2 v3 w2 plus, and so on and so forth. You have to write many terms, and they would result in, that would take a lot of time, and then you have to account for the fact that this Levi-Civita tensor, that whenever you have 1 2 3, it has to be positive, but whenever you have one change, let's say you change 3 and 1, whenever you have 3 2 1 or 1 3 2 or 2 1 3, one change is -1. If you have two changes, it again becomes +1. For example, 2 3 1 and 3 1 2 require two changes from this, right? And another property that if any two indices are same, so epsilon 1 1 2, this would be automatically 0. So since this is this will give you 9 terms and you have to account for them, this is generally lengthy. So why do we follow it? The reason is that it is really helpful in proofs. Okay, now before I go further, I want to again make you note the two useful identities that we will use in these proofs. I won't go into the details of proof of this, so I'll directly write it here, that if you have any Levi-Civita tensor interacting with another one, which could happen if you have A cross B cross C, right? This is the vector triple product. So these situations may arise, and they will arise in the subsequent example that I'm going to show you. So you can write these as combinations of some Kronecker delta functions. So you have epsilon I j k, epsilon mn k, and you see that are the common ones, the repeated index here. And what you do is, basically, to remember properly, you take one, you take this. So im delta jn, all right, minus delta in delta jm. Simple as that. Similarly, if you come across another combination which is epsilon ijk and mnk, oh, sorry, there must be a, sorry, what I meant was kmn. This is also going to give you the same, because it requires two permutations to reach here. Okay. Now, another rule that we have for before we go about proving something is that, let's say you have a vector that you want to prove, v cross w. So this is how you will write it. You'll assign j to this, for example, k to this, for example, and overall vector that comes out should be of I. So you'll write epsilon ijk vj wk. And let's say if you change the notation for a moment, or change the indexes for a moment, by switching these parts. So let's say you want to write epsilon ijk vk wj. If you want to do this, then you have to apply a minus sign, because you did one change. I hope that is clear. Or if you don't want to change here on this side, and you want to change on this side and switch kj, the same logic applies. You have to apply minus sign. So those changes of indexes, if done once and if done twice, you have to add minus and plus sign respectively. That is true for the entire thing, not just the Levi-Civita tensor. Okay. Yeah. And if you do the change again, for example, if you take this and do the change again and switch this again, so it becomes epsilon kij vj vk, then it becomes again plus. Okay. So what I mean by this is that a vector product can be twisted and turned, but you have to play along these rules of changes. It might not be very clear. Why do we want to make our life difficult? We just learned this. Why can't we stick to it? We'll see it. Okay. All right. For example, if you want to prove a curl of a cross product of a vector with itself is 0, what you can do by doing this twisting turning, you can show that it's quite simple. So you have epsilon ijk vj vk, meaning you apply j here index, you apply k, and overall you give I. You write this. You switch the index between j and k, so you make it minus epsilon ikj, and you leave it alone, the other one, because you can't do two at same time. If you do two at same time, then you again, I mean, if you were to do, because this is also a doubt in some students. If you repeat here and also repeat here, that would again give you a plus sign. Although here both v and v are same, so it's inconsequential. But let me just show you quickly. If you have v cross w and you write epsilon ijk vj wk, what I mean by that is that it will be plus if you make changes here and here. I kj vk wj. Okay, so this is something to keep in mind. Okay. All right, so we have this. Now what I'll do is I'll just simply switch this jk, it becomes minus ikj, and you have this. Since v and v are same, you see that a quantity is equal to its negative sign. That is only possible if that quantity is 0. Therefore, the answer is 0. Let's move on to a more involved example of a vector triple product, and you have left hand side to be proven to the right hand side. U cross v cross w should be equal to the right hand side. So let's take it step by step, and I'll show you how to use Einstein notation here. Let me take pen. All right. So first step is to assign the index. So let us assign. So you have UI, and what you see here is that you can assign it. Sorry, the first temptation would be to assign it I, assign it J, assign it K. But I would not advise that because you will run into problems. So please hold on, and you'll see why I'm saying this. Assign it I, and if there are any nested items, any bracketed items, you assign that entire thing, that entire item, as, let's say, J. Or alternatively, I mean, just change, you can make it J, you can make it K, and you can make the whole thing I. Yes or no? Because keep in mind, this entire exercise, the right hand side is a vector. This is a vector triple product, a cross product of a cross product of a cross product. So it will never give you a scalar. So this entire thing will have an index. We choose that index will be I. Inside we give it, let's say, J and K. So we have assigned index, and let me call this bracketed term F. So what I get is simply epsilon I J K uj f k, where my f is v cross w. Now you have to open the structure, and you have to write epsilon I J K uj. Now whatever this is, this should have, whatever f is, its outcome should have the first index as k. And very important point here, that should not do kij, should not do kim. These are all wrong. You should keep in mind never to repeat this index here. Do not repeat it. Take anything but I and j. But you have to start with k because f has k. This will take a while, so you may need to see this part of the video again, and may need to solve some assignment problem. The assignment is uploaded, but I'm sure that you'll grasp it. If you don't, again, in the next class you can ask me and I'll give you another example. Okay, so let's not do the repetition of I and j. So let's say k, l, m. There are many alphabets at our disposal, so this becomes v, l, w, m. Okay, this is the correct way of doing it. Now what you can do, just a second, what you can do is that, okay, just write it more casually, I, j, k, k, l, m. I'm just going to bring it here because, again, the order in which you write things inside the Einstein notation doesn't matter. U, J, V, L, W, M. Now I already told you a property of this, so this would be delta. There is a repetition, delta epsilon ijk, and then this is klm. So let me write it, epsilon ijk, epsilon minus lkm. But again, I can make one more change, and I can write it lmk, right? uj, vl, wm. Now I can use my identity that I wrote here. So this would be delta il, delta jm, the first with first and second with second, minus the alternating ones, I m, delta jl, and then with a bracket, and then you have uj, vl, wm. Okay, you can write them, you can expand them and write delta il, delta jm, uj, vl, wm minus delta im, delta jl, UJVLWM. Okay. Now what do we have here? Okay, so now as we know, the Kronecker delta tells us that I and L should be merged and J and M should be merged. So you can either let L be L or make it I. So I decide to make it I, so it becomes VI. And in JM you can choose either this to make this M or make this J. I choose it to be, let's say, M. So you have UMWM minus I and M are identical, so let's say I make it I, and then J and L are identical, so let's say I make it L, ULVL. I could have also alternatively written this as, so my choice of VL UMWM after this step, and keep this as WI, this let's say we didn't change, ULVL, right? Then that would be a mistake. Why would that be a mistake? Is because see, if you write back in Gibbs notation, this would give you VL, and this is a dot product, so let me just abuse the notation a bit just to give you a physical picture. U dot V. So first of all, this did not prove the vector triple product, because as you see here, V and W, they are both vectors, but they should have the same index, although they are separated by a minus sign. So this entity is different and this entity is different, but this whole left hand side is of index I, right? We decided it. So we have to keep in mind that the entire equation, which is one vector equals to another vector minus another vector, they all should have the same index. Okay, so it will be better that way. So I will not do this thing, and I will be aware that what sits here is some I. What sits on the left hand side, I have decided that it is I. So I'll keep using this, and I'll have VI U dot W minus WI dot V. And I mean, since this is a free index, this is a vector, let me just write it. Yeah, so I think we have this. So V U dot W, V U dot W, W U dot V, W U dot V. Okay, does the distributive property hold for a cross product? Yes. So you have U plus V vector addition crossing with W. Yes, it holds. Does the associative property hold? U cross V cross W? This I'll leave as a homework to you. There is an identity of scalar triple product. Again, you can prove this using Einstein notation, but also can you interpret this physically? If you recall from the class, I mentioned that cross product is area of parallelogram, and the dot product is the rectangle which is projected, or sort of projected rectangle. So it's not a surprise that if you have, let's say, B vector and then C vector crossing, and then there is a theta angle and there is a parallelogram, and this area is there, right? And you have another vector now dotting with this. So let's say this is another vector dotting with this. So the projection of this onto this vector would result in another dimension, and that would yield to a volume of parallelepiped. Now you could have done these cross product between B and A and then taken the projection of that parallelogram onto the C vector. That would result in the same volume, right? That's why just from physical intuition you can just think that okay, the scalar triple product identity should hold, but you should also prove it using Einstein notation as an exercise. Okay, now I'll move on to tensors. We've covered already some parts, so this will be quicker. A tensor is an element of 9 numbers if it is a second order tensor. In Einstein notation, we will denote it as, in Gibbs notation, it will be this, or some may write this, but this will be written as Aij. I'm not going to write Eiej because again it becomes really bulky later on. Now what it physically means, a vector, we knew that it had a direction and magnitude. A tensor is a configuration that relates vectors. A very good example of this is the linear transformation that you are all aware of, and that transformation we showed that in a 2x2 simulation. So we took A as 2x2 matrix, and we took this example and we saw how X is transformed to B subject to the various elements inside the A matrix or the A tensor. It essentially, the A distorts the space such that X transforms to B. And I urge you to see the variation of each element, all the 4 elements in this 2x2 simulation. Just change them and see what happens. Make them negative, make them positive, make them fractional, 0.5 and 2, see what happens. Okay, coming to quickly to the Einstein notation of dot product between tensors and vectors, which is very simple now. So you have, let's say, let me rub this up. Let's say you have A dot, simple linear transformation representation. How would you write it in Einstein notation? The rule is following, that you have to consider the closeness. So for example, the tensor is made up of 2 indices, and then you're gonna apply an index to this, but you have to be aware of the dot product. Yes, so what it should it be I or should it be J? It should be J, because the X is on the right of this. If I had written X dotted with this, then you would write it as Xi Aij. So the first index of the tensor would be repeating, or alternatively you could write it as Xj Aj. The first index is repeating. Both are equivalent. Okay, in this case you have Aij Xj, and this should be equal to, again, if it was a class, I would ask a question, would it be Bi or Bj? And the answer is that it is Bi. It cannot be Bj, because the repeated index is already summed over, right? So it will be Bi, and again Bi is a vector. Okay. All right. Just a quick one, if you are wondering what a third order tensor and higher order tensor would look like, they would just nest vectors inside tensors. So this is how a third order tensor would look like. It will be 3 cross 3 cross 3. This will have 27 elements. All right, so we'll end this now with the description of position vector. So position vector is an important aspect in transport phenomena, especially in fluid mechanics part, that we will define any location in space, let's say that is XYZ, and that is represented by a position vector R, where R can be written as, or sometimes I may also write it as X vector. I'll try to be consistent, but they are so interchangeable within the textbooks and reference books that it can be a bit confusing sometimes. But if I'm telling you up front, I hope this clarifies. So basically it means that you have this location with XYZ coordinate multiplied by the unit vectors, and that's all. Apart from position vectors, you have scalar field. Scalar field, for example, one of the example is a temperature map in the system, heat transfer through a slab or diffusion through a liquid medium. They all have this profile, right? So that temperature profile is a scalar field, meaning a scalar quantity like temperature or concentration varying in space. So temperature can be varying in X, Y, Z and time. Hmm? If you want a spatial scalar field, if you want to define it, spatially varying scalar field, then you would have temperature varying in x, y, z. Sometimes in textbooks it is also written as TR, temperature varying in along the various position vectors. So they all mean the same thing. Uh, there is also something known as the spatial vector field, just like a spatial scalar field. One of the example is that we've already seen before is a water flowing through pipe. So you know this parabolic pressure driven profile, and we write this as v vector is equal to some formula that we'll derive later in the course into ex plus 0 into ey plus 0 into ez, right? So this is a spatial vector field where the ex component varies in this. So to be precise, it would be some function of y into ex plus 0 ey plus 0 ez. So there is spatial variation along with the unit vectors. Some simple properties here. Scalar vector fields added and represented like this. You can freely do scalar multiplication to these scalar vector fields. So alpha, which is a function of r, can be multiplied with v. So meaning, let's say you have a velocity profile like this, and you want to do some operation and multiply 2 to it, you can do so. If you want to multiply a function of some x to it, you can also do so. So not just alpha, but alpha as a function of space can also be multiplied. Again, whatever you learned about the vectors also applies to spatial vector fields. V dot u, where v and u both are spatial vectors field, they can be dotted just like a usual, vectors. And here we'll look at gradient of a scalar field, where f is a scalar field which varies in x, y, z, let's say. And since it varies, if we want to take a gradient of field, we're essentially asking where does it increase or decrease? Hmm? And we know very well that in one dimensions, gradient determines the slope of a function. Hmm? In two dimensions, very similarly, it tells us the direction of maximum increase. A very quick way to see this is the following. That let's take the first linear function. So let's say f is equal to x plus y. And we'll take the 2D example only for simplicity. And this is your y and this is your x. If you want to now plot a sort of a contour plot, meaning you color the values on this xy plane, you will see that as you keep increasing x and y, so let's say keep increasing in this proportionally, you'll see that a value of the function f will keep increasing in this area, and it would be somewhat lesser and somewhat less than 0. So here f will be 0, here in this area f will be something, in this it will be a bit more, and here it will be a bit more, and so on. It will keep increasing in this direction. And similarly, you can extend this in other quadrants also. I'm not going to do that, but just you get the idea. Now, if we focus on only in the first quadrant, um, the gradient. So if you take the gradient of f, and with this we will also see the Einstein notation. This could be written as del if or dou f by dou xi. So it gives rise to a vector field because scalar field doesn't have any direction, but as soon as you take a derivative, the direction is associated because we are saying where are we observing the trend, in which direction are we going to observe this growth or decay of scalar field in space. Okay, so if we do that for this particular example, we get um, ex plus ey plus 0. There is no direction. There's in z direction there is no variation in this example. In vector form in which you are aware or more comfortable with, this is 1, 1, and 0. Now, if you want to pictorially see how does this look like, if you want to plot it on XY plane, this essentially would point in this direction, the direction of maximum change. Okay, so this would be your arrow, which would signify the direction of maximum change, or direct where, yeah, or the it will direct you towards the increase of f. That's more appropriate to say. Directs us towards increasing f. You can take the second example of a quadratic field now, because what we see here is the gradient of f in the previous example is just a number. It could also be a function of space. Gradient of a scalar field could also be a function of space, for example, for this x square plus y square. And now I'm not plotting this here because I've already plotted on the right. So this is the function f x square plus y square, meaning as we increase x and y, the function is going to keep increasing. As x and y decrease, it's going to keep decreasing. So it is like a radially symmetric hole, or a pit. And as you go away from this, from the center, it keeps growing rapidly. So naturally, you would imagine that the direction of increasing f is going to be in this direction, sort of radially outward. Let us see if that is the case. Let us evaluate grad f. This would turn out to be uh, dou f by dou x1 ex, sorry, dou f by dou x ex plus dou f by dou y ey plus dou f by dou z ez. This does not matter because there's no z component here. So we get 2x, 2y, and 0, right? If you want to write it in your well-known vector form. Now, if you see here, this points in the, I mean, if you take the 2 out, this is x, y, and 0, meaning that if you take, so let's take any other color here, um, meaning that if you put any values, let's say x equal to 1, y equal to 1, the vector is going to be 2, 2, 0. Again, it's going to point in this direction. If you're going to take x equals to uh, -1, so let me rub this and show it more properly. If you take +1, +1, so what you get is at x equals, so this is your coordinate axis, at x equals to 1 and 1. At x equals to 1, y equals to 1, right? Your f vector, x component is in this direction, y component is in this direction, resultant is in this direction, right? So you have, okay, this checks out. So let's check at any other location. If you were to measure this vector at x equals to -1, y is equal to +1, then your vector would be -2, +2, 0. Meaning, so you would be somewhere here, x equals to -1 and y is equal to +1. This would be pointing in negative direction. This would be pointing in the same strength in positive direction. The resultant would be somewhere here. Okay, and similarly, you would find the resultants in each of these directions. So you have radially outward uh, direction of increasing f, which makes sense with this contour plot visually also. Now let me remove all this and I'll do the same exercise for an opposite function, a hill type of function, where I'll just put a minus sign into this function, and what you get is this. And naturally, you will see that the maximum rate of increase, sorry, it would be inward, right? So the hill rises and it's highest at 0, 0. I mean, you can easily see this by just calculating f, and it will be just inward. It will be -2x, -2y, and 0. You calculate it at x equals to +1, y equals to +1. what you see is this one plus 1. The grad f will be minus 2, 0. So at this location, the x direction is like this, the y direction is like this, and the resultant vector is inward. And similarly, all the vectors you will find at each location will be inward. Okay, so I hope it clarifies the way to calculate gradient of a scalar field and the physical interpretation of it. Let's move on to the divergence, and here we're going to look at a 2D example. There is below is what you see is a 2D vector field. I've kept a question mark here. Um, right? Yeah. Um, can you take a moment and guess what sort of vector field would give rise to such a flow field in XY space? So since it's a vector field, it will be associated with some sort of movement. That's why you see the uh, sort of video going in loop. And as you see, as you can observe, that as you go in this direction, the arrow length keeps increasing. If you go in this direction, the arrow length is the same, and also there is no flow in the vertical direction. So if I were to guess this vector field, I will say this vector field um, is it a function of y? No. Is it a function of x? Yes. So there is a non-zero x component to the flow field, meaning there is a non-zero flow field. So this term, first term will be non-zero, and and it seems to be some increasing function of x. So for simplicity, let's say I'll guess this is x. Hmm? As we go in x, the strength of flow field in x increases. That's what this is saying. In y direction, there is no flow field, so I'm going to put it 0. In z direction, there is no flow field, so I'm going to put it to 0. So I would guess that this is xex, this vector field. Okay. Um, and now I want you to focus, because here we are calculating divergence. Divergence of a vector field, mathematically speaking, would result in a scalar because it's a dot product between two vector entities. So you have dou vi by dou xi in Einstein notation, and if you want to expand it, it would be dou v1 by dou x1 plus dou v2 by dou x2 plus dou v3 by dou x3, or in Cartesian you could write it as dou vx by dou x plus dou vy by dou y plus dou vz by dou z. All right. If we want to calculate the divergence for this flow field, we would get mm, divergence of xex. So you can clearly see that there is no y and z variation. So what you would get is just 1. So divergence of v in this example is 1. Meaning what? What is now? So you may be wondering, what is now divergence of v? If it was -1, what it would be? If it was 0, what it would be? So an easy way to visualize the divergence is to see, is to map a circle, as you can see here in the orange, sorry, in the white line. And if you can observe the amount of flow coming in versus the amount of flow going out. So it gives you an idea of what is the net outflux from this hypothetical circle. You can shrink the size of this circle if you want to calculate the divergence at a point. So what this is that if you have a scalar field, or sorry, if you have a vector field, and this vector field is a continuous vector field, it is valid at each point because we are in the continuum approximation. At any point that you want to calculate the divergence, you go and you point and you assume a very, very small circle, and you sort of ask, is there a net inflow or outflow? And the physical meaning of this is how much is out minus in here. So if it is a positive quantity, then it would be there is net outflux from this stream. Do you see a net outflux from this white circle in this example? I certainly see so, because if you look at the left hand side of the circle, so let me highlight it, the left hand side, the flow is slowly coming in, but on the right hand side, it will have a bump because the flow field is getting accelerated as we go in X. So out, the rate of outflux from this will be always higher than the influx. Okay. In the next example, oh sorry, I think I pre-explained a bit. Uh, so here I make this dashed circle a bit smaller to raise the point that divergence is a point-wise entity that we calculate in the xy plane. So the flow of V, so that's right here, flow of V out of the infinitesimally small point is greater than flow inside the circle. So out is greater than in, and therefore you have del dot V greater than 0 for that particular example of this flow field. V is equal to XEX. All right. I should also point out that uh, although it seems in that example, sorry, in that example, it seems like it's a quantity 1. If I would have taken any other example, it would turn out it could be also a function of x, y, and z. Okay, so if you take a divergence of a vector field, it gives you a scalar field in general, meaning it gives you a scalar map. In that particular case, it is 1 everywhere in the domain. So wherever you point and wherever you select, you're going to find that the divergence is equal at each place. Yes. Now you can just expand this domain and apply it to 4 quadrants. This is how this vector field would look like. Um, x comma 0 comma 0. If you take the divergence, it's going to be 1 everywhere in this domain. There is always this net spreading out. Domain is a source at all points. At any point you pick, it's acting as a net source. All right. Now, in fluid mechanics, for example, when you deal with vector fields, and the time will come for that, you will see that some places can act as a source and some places can act as a sink. So then the divergence could also change in space. So by that I mean that some places divergence could be greater than 0, some places could, sorry, should be greater than 0, it could be here less than 0 for converging field and diverging field and so on. Okay, so you would see various examples. Another very good example of a 3D case. So until now we talked about this. This was the 2D case. In 3D, if you want to imagine, you can imagine gravitational fields around Earth and Moon and how they sort of act towards each other. And if you were to calculate, if you were to point out anywhere in the flow field, you would find the divergence, how much of the gravitational field is sucking in versus letting out. Okay, so this would be a nice example of a three-dimensional vector field and its divergence. In this case, both are acting as sinks, in meaning in both cases there is more in versus out, so the divergence will be negative. Okay. Now we're going to talk about a similar example. This I already worked out here, so let me rub this out. Oops. So in this special case, let's say that the vector field is made up of the gradient of scalar field, what we found in the first example. So that if you plug in the divergence, so let's see, if you want to find the divergence of such a vector field which is already a gradient of scalar field, then it would result in Laplacian del square f. It would result in d square f by dx square plus d square, if it's Cartesian, d square f by dy dou y square plus dou square f by dou z square. It should be partial derivative. And to see that, you can just clearly use Einstein notation, and you can say it's dou by dou xi, or you can write dou I f, or you can write dou by dou xi of dou by dou xi of f. Now, if you want to use the Einstein notation, the summation rule, if the indexes are repeated, you can sum them, meaning dou by dou x1 dou x1 plus dou f by dou x2 dou x2. Of course, this is redundant, so I can just do dou f by dou x3 square. For Cartesian, these two are identical. So you get a Laplacian. What does this mean physically? It means it tells you how much curvature is there in the flow field. Oh, sorry, how much curvature is there in the scalar field. Take the example of f is equal to x plus y. Of course, it will have no curvature. It is a linear field. So if you're going to calculate del square f, it's going to be 0 because it's linearly increasing. So there is no curvature. But if you take the example of x square plus y square, then you're going to find the curvature, right? All right. We move on to our final example of curl. Um, so now, just to quickly see this, what you can do is you can imagine a vector field, um, and then place a circle or a hypothetical circle in it, as I have placed here, and you would see that it would start to rotate because the velocity that it would experience, or this hypothetical flow field of this V that it would experience on the top surface, would be less than at the bottom surface, or at the bottom point of this ring. So naturally it would tend to circulate. If you were to displace this below and place this ring here, it would rotate in the opposite way because the velocity here is high, it's low. So here it would rotate in, it would point in the negative direction downward, and here, okay, so in both cases it would be negative. In both cases, the circulation would be clockwise. Okay. Now this is a clockwise rotation axis pointing in the negative z direction or into the plane. If you want to denote curl of a vector field in Einstein notation, but what I mean by this, sorry, is that it gives you the extent of circulation in the flow field. Again, as we did with the divergence, to send a message across that the curl is going to be a vector quantity, but it's going to be a pointwise quantity. So here we made a bigger circle, but once we get the idea, we're going to shrink it, and we'll say that we are finding curl at each point when we're taking this, when we're doing this operation. We're finding the tendency of rotation of this fluid flow at each of these points. Okay. So let us we find out an example. So in the Einstein notation, we have um, curl of cross product of two fields is epsilon I j k. I mean, you assign it j, you assign it k, and the overall vector field, since it's going to be vector I, we're going to assign it. You can assign the other variables, but just respect the rules. Okay. This will be grad j v k. Okay, this is how you would write in Einstein notation the curl of a vector field. Okay. Now here, since again curl will be negative in sign here because it tells you the direction in which it is pointing. So if it was pointing upward in the positive z direction, then the curl would be positive, which would be true if you would have reversed this flow field. Or the circle was rotating in the counterclockwise direction. Okay. Let's look at an example of proving using Einstein notation that curl of a gradient of scalar is always zero. In physical sense, it means that climbing up and down the hill will not induce any rotary motion. What do I mean by that? Is that you know now well that gradient of f tells you like the direction of increase or decrease. So it gives you some sort of slope in 1D, 2D, 3. And a gradient of scalar field is a vector field. So it gives you a flow field of a slope of some kind. And when you're taking a curl of this entire thing, sorry, if you're taking a curl of this vector, you are saying that I'm going to place a small point-like circle in this flow field, like a paddle wheel. So one can imagine this example for better case that you have a flow down an incline caused by the gradient of f. If you're going to place a paddle wheel, all that paddle wheel is going to experience is downward translation, but not rotation. So such a flow, if you were to place this wheel with its axis of rotation perpendicular to the face of this plane, so you're not setting it up for rolling motion like a typical tire would on top of a hill, but you're sort of placing it to experience the flow field. So you're facing it uh, with its face down on the plane. I hope I'm getting clear. What I mean by this is that I'm not placing it like this so that it rolls down and goes forward. Of course, it's going to roll down like that, but we want it to roll or not roll because of the flow field. So we're going to tilt it mm, and place it like this, so that whenever if it rotates or not, it points its direction of rotation either out of this plane or into the plane of the slope. Okay, and in this case, it will not rotate. This is what, in physical sense, the curl of gradient being zero means. Okay, so let's prove that it's always zero. And using Einstein notation, it's pretty simple. You can just write epsilon I j k del j, this bracketed term k. Okay, so we assigned this j, we assigned this bracketed term k, and we assign this everything as I, and therefore we write this. Now let's open the bracket, so we get epsilon I j k del j gradient of f. So we have del k f. Okay, um, epsilon I j k dou by dou x j dou by dou x k. I'm just writing it in the conventional form. Nothing special here. Now I'm gonna switch j and k. Okay. So what I'm gonna do is I'm gonna switch. I can either switch here or I can either switch here by using the rules of Levi-Civita. So I'm gonna do switching here using Levi-Civita or cross product rules. I'll get minus epsilon I j k dou square f dou x k dou x j. Yes or no? But now I'm going to use the rules of mixed derivative property. What is mixed derivative property? That del square f by dou x dou y is equal to del square f by dou y dou x. It doesn't really matter how you write it, how you take the derivative of. So I can flip this again back using this rationale, and you'll see what happens. So the minus sign won't change because I'm using the rules of MDP, and you have epsilon ij k dou square f by dou x j dou xk. Okay, so now you have a situation where this entity is equal to negative of the same entity, and that could only happen when they are zero. Okay, hence curl of a gradient of scalar field is zero. Okay.